Hello, welcome to the first tutorial on networks, and we're going to start off by talking about what is a network. A network is basically a collection of objects connected in some way, and in the case of this topic we're going to represent the objects as little circles, which we're going to call them nodes. So these things here, we're going to call them nodes, and they're going to be connected by some lines that we're going to call arcs. Okay, so networks are made up of nodes joined by arcs, and usually the arcs will have some kind of value on them indicating the distance between the nodes. So for example, I can say the arc length here is 3, arc length here is 4, 5, 7, and so on. But for our purposes right now, we don't have to worry about arc length. Okay, each node can then be classified as an odd node or an even node. So if you have a look at this node here, this is an even node. Okay, but if you have a look at I'm just going to join these two nodes with another arc. If you have a look at this node here, this is an odd node. So what is the difference between even and odd? How can we tell? An even node has an even number of arcs joined to it. So you can see we have 1, 2 arcs joined to it. Odd node has an odd number of arcs. Joined to it. So we have 1, 2, 3 arcs joined to it. And you can also say that this node is a 2 node. And this is a 3 node. Right, because there's 2 arcs there, 3 arcs here. And another definition you might find useful is path. Path can be a series of arcs. So if we define a path as let's say from this circle here to this circle here, we have to use 2 arcs to get to it. So okay, now we're going to talk about whether a network is singly traceable. And to test whether it's singly traceable, I'm going to start here at this circle. I'm going to go to the left, down, up, right, down. So I have just proven to you that this network is singly traceable because I went through all the arcs without repeating the same arc. Now something that might not be singly traceable, let's try and see if that's singly traceable. So I'm going to start here, 1, go down to the right. Alright. As you can see, it's not singly traceable because I can't go through the same arc again. So I've arrived at this point, I can't go anywhere, so that leaves this one not traced, so it's not singly traceable. Now a quick way to test whether a network is singly traceable is to see how many odd nodes and even nodes that it has. Okay, so how do we determine if a network is singly traceable without trial and error by drawing all over it? Well, here are the strategies for determining whether it's singly traceable. It will be singly traceable when, number one, it has no odd vertices. So, for example, in our first network, if we just had 4 nodes, 1, 2, 4 arcs. Each of these nodes are even. Each of these nodes are all even nodes. So there are no odd vertices, and you can see that it's very easily singly traceable. If it has 2 odd vertices, it's also singly traceable, as the case here. We have this one is odd, and this one is also odd. So we can start at an odd, singly trace it, and end up at the other odd. In all the other cases, it will not be singly traceable. Okay, so all other cases not singly traceable. So hopefully that gives you a quick way of determining whether a network is singly traceable without having to do it via trial and error. Okay, now we're going to talk about how to draw a matrix from a network. And this is actually pretty easy, even though when people talk about matrices you think of something complicated, but it's actually pretty easy. So let's have a look at one of the networks, and this is the network, and what we're going to do is create a numerical representation of this by drawing a matrix for this network. Okay, so to draw a matrix, basically there are 4 nodes here, so I'm gonna write each node as a heading, both the column headings and the row headings, and I'm gonna draw a big bracket. I'm gonna draw a big bracket. Okay, now from A to A, if you have a look at my node, there is no connection going from, no arc going from A to A, so that would be 0. Now from A to B, there is 1 arc, so I'm going to put 1. There is nothing connecting A to C directly, and there is no arc between A and D, so 0. So basically a matrix is simply saying how many arcs are connecting from one node to another. From B to A there's 1, from B to C there is 2, from B to B there is 0, from B to C there is 2, from B to D there is 1. From C to B there is 2, C to A there is 0, C to B is 2, C to C is 0, C to D is 1, and lastly for D, D to A is 0, D to B is 1, D to C is 1, D to D is 0. So this is our matrix. And usually when we write the matrix, we don't write the headings. So this part is usually omitted. So when you see a matrix like this, and from this matrix you can draw this network without knowing that the nodes are called A, B, C, D, A, B, C, D, and on the left hand side is from, on the top is to, and so on. You are given this network and you're given this matrix and you can be asked to redraw the network. So for example, if we didn't have any of this information, so if I blank out all of this and I asked you, by giving you this matrix, draw a network for the above matrix, then you should be able to just do the A, B, C, D yourself. A, B, C, D, and figure out that we have 4 nodes, so A, it doesn't even matter how you draw it, A, B, C, D. A to B is 1, B to C is 2, B to D is 1, and C to B is 2, C to D is 1, D to B is 1, D to C is 1. And you can see that this is pretty much exactly the same as this network. Even though B and C have been switched around, it still works exactly the same way. This network has the same matrix as that network. Okay, now let's talk about loops. Now, for example, in this same network, if I add a loop at a particular node, okay, let's say on D, I now have a loop going from D back to D. Now, what happens is, sorry, that might make it a bit confusing. I'm just going to write the word D somewhere else. So what I'm going to do is on the matrix now corresponding to this network, I will then have to change the number 0 to 2. Now why is it 2 and not 1? Because from D back to D, there is 2 ways you can do it. You can either go this way or you can go this way. So because there are 2 ways of going from D to D, you have to put the number 2 there in the diagonal. So you will see with all of these matrices, but by the way, matrices is the plural for matrix, that they are all symmetrical across the diagonal. So if this is a diagonal, okay, this is a diagonal, and we have the top right section here and the bottom left section here. These 2 sections are symmetrical. Okay, so you can see we have 1, 2, 1 and a 1, 1, 2, 1 and a 1. So this side is a mirror image of this side. And that is a characteristic of networks, of this type of network, which we call non-directed networks. So this network here is a non-directed network. So when does a network become directed? Well, a network becomes directed when we start drawing arrows on the networks. So using this network here, I'm going to draw some arrows on them. So I'm going to say A can only go to B. I'm going to draw an arrow there, draw an arrow here. Now as soon as you start drawing arrows on the network, then it becomes a directed network. Okay, so for a directed network, what happens is the matrix will no longer be symmetrical. So we're going to have to make some changes to our network here. So from A to B it's 1, but from B back to A is 0. So I'm going to change this number to 0 now. Right, the reason is for this arc here, you're only allowed to move in one direction. So you can't go from B back to A. And same thing here, we go from B to C is 2, right, because there is no there is no restriction on the direction of this arc. But going from C to B, there is only one line. So C to B is only 1. Okay, and then D to B is only 1. D to B is 1, but B to D is 0. So B to D is 0. B to D is 0. A to B is 0. Oops, B to A is 0, A to B is 1, yep. D to B is 0, B to D is, hang on a second, D to B is 1, this should still say 1, B to D is 0. So when you're doing the matrix for directed network, it's very important that you remember these are the from nodes and these are the to nodes. So from B to A is 0, from B to D is 0, from C to B is 1, from B to C is 2. Okay, so once you have drawn the matrix for the directed network, you will see that it's no longer symmetrical. So this is a diagonal, and we can see that these numbers are no longer symmetrical to these numbers. So directed network, they are not symmetrical across the diagonal. And if we have a loop, okay, if we have a loop at one of the nodes, let's put a loop around B. And let's put a direction on that. So from B to B, we are allowed to have 1 on the diagonal. Whereas for a non-directed network, on the diagonal, we're only allowed to have even numbers. On a directed network, we're allowed to have odd numbers. And that is because for a non-directed network, each time you draw a loop, that's 2 ways. Whereas if you draw a loop on a directed network, then you put a direction restriction on that, then you can only have you could get a 1 or 3 on the diagonal. Okay, so hopefully from this tutorial you've learned a little bit about networks and how to draw matrices for them. See you in the next tutorial. Thanks for watching.